Welcome to For Science Salah Lotfy channel. Today we introduce exciting Egyptian research that could change how laser materials are made, efficiently and at a lower cost. A research team at the National Center for Radiation Research and Technology has developed ytterbium-doped phosphate glass, a promising alternative to expensive crystal laser materials. When this glass was exposed to gamma radiation, it not only became more stable but also delivered stronger laser performance. The secret lies in healing microscopic defects, making the material more efficient, reliable, and cost-effective. This innovation could support strategic fields like telecommunications, medicine, and defense, and reduce Egypt's dependence on imported technology. This is more than a scientific study. It's a step toward building Egypt's future in advanced laser technology. To learn more about this remarkable research, watch the full episode only on For Science Salah Lotfy channel.
Welcome to For Science Salah Lotfy channel, where science meets curiosity. في هذه القناة لا نكتفي بعرض الأبحاث العلمية، بل نترجمها إلى المعرفة التي تصل إليك أينما كنت. Our mission is to make global scientific research understandable, accessible, and multilingual. جميع الفيديوهات العلمية هنا مترجمة إلى اللغة العربية، بالإضافة إلى لغات عالمية أخرى. French, Spanish, German, Urdu, and more. Because science speaks every language. نعم. العلم يتحدث بكل اللغات، ونحن نحرص أن يصلك بلغتك. If you're passionate about science, you're in the right place. اشترك الآن وابدأ رحلتك مع العلم خطوة بخطوة. For Science Salah Lotfy channel, العلم للجميع.
Welcome to For Science Salah Lotfy channel. Today we highlight an outstanding Egyptian research published in the Journal of Materials Science, Materials in Electronics, 2022. Physical and structural properties of gamma-irradiated ytterbium phosphate glasses as a nominated lacing material. It was conducted by Professor Dr. Omnia Sallam and Professor Dr. Nagia Elalaily from the Radiation Chemistry Department, National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, Cairo, Egypt. The research focuses on developing ytterbium-doped phosphate glass, a promising and cost-effective alternative to conventional laser crystals like Nd:YAG. Phosphate glass is known for its high transparency, low melting point, thermal stability, and the ability to host rare earth ions. Ytterbium ions, Yb3+, are especially interesting because they provide high energy conversion efficiency and have a simple two-level structure, which makes them ideal for stable and efficient laser operation. To enhance the material's properties, the team exposed the glass samples to gamma irradiation at different doses. This innovative approach aimed to improve the optical behavior of the material and reduce photodarkening, a major problem that causes energy loss in laser systems. The results were remarkable. Two main absorption bands were identified at 237 nanometers in the UV range and 975 nanometers in the near-infrared range. When the glass was irradiated, the UV absorption decreased while the infrared band became stronger, proving that radiation helped heal internal structural defects. At a concentration of 3% ytterbium oxide, the glass showed the best performance, stable structure, higher refractive index, and enhanced resistance to photodarkening. This means the glass can act as an effective laser gain medium. Its fabrication is simpler and less expensive than growing single crystals, making it ideal for industrial applications. This research has strong economic and technological implications for Egypt. Producing laser glass locally can reduce dependence on imports, support strategic industries, and position Egypt as a regional leader in laser material development. To explore the full details of this groundbreaking study, stay tuned to For Science Salah Lotfy channel. Don't forget to like, share, and subscribe to follow the latest in Egyptian scientific research shaping tomorrow's technology.
Welcome to For Science Salah Lotfy channel. Today, we are diving into a fascinating piece of scientific research conducted at the National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority. This study explores a new generation of lacing glass materials that could reduce costs, boost performance, and strengthen Egypt's technological independence. Laser technology technologies today rely heavily on expensive single-crystal materials like Nd:YAG, but this research focuses on ytterbium-doped phosphate glass, a promising alternative. The researchers prepared glass using a specific chemical composition, P2O5, Na2O, Al2O3, PbO, and different concentrations of Yb2O3, that's ytterbium oxide. Why ytterbium? Because Yb3 plus ions have high energy conversion efficiency, low background absorption, and simple energy level structure. This makes them ideal for producing stable and efficient laser emissions. And why phosphate glass? Because it is transparent, thermally stable, has a low melting point, and can host a high concentration of rare earth ions, all at a lower cost than traditional crystal growth techniques. When the researchers tested the optical properties of this glass, two main absorption bands appeared, one at 237 nanometers, linked to UV absorption and photodarkening defects, another at 975 nanometers, directly related to laser transitions of Yb3 plus ions. But here's the remarkable part. When the glass was exposed to gamma radiation at doses of 0.25, 1.25, and 10 kilogray, the UV absorption band decreased in intensity, and the 975 nanometer band became stronger. This means gamma irradiation actually helped heal structural defects in the glass and improved its laser performance. Moreover, photoluminescence measurements revealed stable and broad emission around 990 to 1050 nanometers, perfect for many laser applications. At a concentration of 3% Yb2O3, the material showed the best performance. A stable structure with no clustering of Yb ions, improved refractive index, and better resistance to photodarkening. This makes the glass a strong candidate for use as a laser gain medium. Compared to crystal-based lasers, phosphate glass offers easier fabrication, lower costs, and flexibility in shape and size. The use of gamma irradiation to enhance its properties is an innovative approach that could be applied at an industrial scale in Egypt. The economic potential is significant. Local production of laser glass materials can reduce Egypt's dependence on costly imports. It can support strategic industries, including telecommunications, medicine, and defense. And it positions Egypt as a regional hub for laser material development. This research is not just about new material, it's about building a scientific and industrial foundation for the future. To discover the full details of this groundbreaking work, stay tuned to For Science Salah Lotfy channel. Don't forget to like, share, and subscribe to our channel. Follow us to explore how Egyptian research is shaping the future of science and technology.
Welcome to For Science Salah Lotfy channel. Today we're diving deeper into a remarkable Egyptian research published in the Journal of Materials Science, Materials and Electronics, 2022. This study, led by Professor Dr. Omnia Sallam and Professor Dr. Nagia Elalaily, explores how ytterbium-doped phosphate glass can be developed and improved using gamma irradiation to create an efficient, low-cost lacing material. This work combines advanced materials science and radiation technology, positioning Egypt at the forefront of innovative laser material research. Let's start with the fundamentals. Phosphate glass is known for its high transparency, low melting point, thermal stability, and excellent chemical and mechanical properties. Unlike crystals, which are costly and complex to grow, phosphate glass is easier to fabricate and more cost-effective. It can also dissolve a high concentration of rare earth ions, making it perfect for laser applications. Among rare earth elements, neodymium has been widely used for laser materials. But ytterbium ions, Yb3+, offer even higher energy conversion efficiency, lower background absorption, and a simpler two-level energy structure, ground state 2F72 and excited state 2F52. This means less energy loss, higher photoluminescence yield, and improved laser performance. However, there's a challenge. When ytterbium-doped glass is pumped in the near-infrared and exposed to UV light, it suffers from optical losses known as photodarkening. Scientists believe this happens because of two main reasons. 1. Charge transfer processes between oxygen and Yb ions, creating color centers and unstable valence states. 2. intrinsic defects in the glass structure like oxygen deficiency centers, ODCs, and non-bridging oxygens, NBOs. When YB ions form clusters of 3 to 7 ions, they enhance the formation of these defects under UV exposure, increasing photodarkening. And since photodarkening reduces laser efficiency, the research aimed to minimize this effect through smart material design and radiation treatment. The researchers prepared phosphate glass with the following composition, where X FAR 0.1, 1, and 3 mol% of YB2O3. They used the traditional melt quenching method to form the glass and then exposed the samples to gamma radiation at different doses. The goal was to see how radiation affects the optical absorption, photoluminescence, and defect structure of the material. Results showed that the strong UV absorption band at 237 nanometers associated with charge transfer shifted and decreased in intensity after irradiation, indicating that some defects were healed. Meanwhile, the infrared absorption around 975 nanometer increased, which is a positive sign for laser performance.
Welcome back to For Science Salah Lotfy channel. In our previous segment, we introduced a remarkable Egyptian research study on ytterbium-doped phosphate glass and its potential as a lasing material. Today, we're moving one step further, diving into how this innovative material was actually prepared and analyzed in the lab. This experimental work reflects the precision, scientific depth, and advanced research capabilities at the National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority. The glass samples were prepared using the melt quenching technique, a widely used and cost-effective method for producing optical glass materials. The chemical composition was carefully designed as, with X, BUSH 0.1, 1, and 3 mol% of ytterbium oxide. The researchers used high-purity reagents, NH4H2PO4, Na2CO3, Al2O3PBO, and YB2O3, 99.99% sigma Aldrich, to ensure maximum purity and stability of the final glass. This careful selection of raw materials is crucial because even trace impurities can strongly affect the optical properties and laser efficiency of the glass. Once the glass samples were prepared, they were examined using high-precision instruments. UV visible NIR spectrophotometer, model V770, Japan, was used to measure absorption spectra from ultraviolet to near-infrared. This is essential to understand how the glass interacts with light. Fluorescence spectrometer, JASCO FP6500, Japan, was used for photoluminescence studies at room temperature. A xenon lamp served as the light source, with a scan speed of 0.1 s, step length of 0.25 nanometers, and slit width of 0.2 nanometer. These settings allowed for highly accurate detection of emission behavior. ESR spectrometer, Bruker ER4102, Germany, was used to detect paramagnetic centers inside the glass. This helped the team understand how irradiation influences internal structural defects. Additionally, gamma irradiation was performed using an Indian cobalt-60 gamma cell with a dose rate of 0.99722 kg/h at room temperature. This controlled exposure is key to studying how radiation heals or alters defect centers in the glass matrix. In parallel with the experimental measurements, the team carried out theoretical analysis to determine essential physical and optical parameters. Optical bandgap, e.g., and Erbach energy, EU, were calculated from UV absorption edges using the Davis and Mott model. These parameters provide insights into the electronic structure and disorder in the glass network. Refractive index was determined using multiple models, including Kumar-Singh, Moss, and Reddy-Saka relations, giving a more comprehensive picture of how light travels through the material. Other critical parameters included density, molar volume, polarizability, optical basicity, optical electronegativity, transmittance, reflection loss, and dielectric constants. Each of these properties plays a vital role in determining how efficient the glass can be when used as a laser gain medium. What makes this experiment impressive is its combination of advanced material preparation, state-of-the-art optical characterization, and rigorous theoretical modeling. This approach provides a complete understanding of how ytterbium-doped phosphate glass behaves under gamma irradiation and how to optimize it for high-performance laser applications. Such work is not only scientifically valuable, it is strategically important. Developing laser glass locally in Egypt can reduce import costs, support defense, medical, and communication sectors, and position the country as a regional leader in photonics. To discover how these experimental results transformed into real optical performance enhancements, stay tuned for the next segment on For Science Salah Lotfy channel. Don't forget to like, share, and subscribe to support Egyptian scientific research and innovation.
Welcome back to For Science Salah Lotfy channel. We explored the fundamentals of ytterbium-doped phosphate glass, the experimental preparation methods, and the advanced characterization techniques used to study its structure and behavior under gamma irradiation. Today, we move to the heart of the research, the results and discussion. This is where the story of light absorption, defect healing, and laser potential comes together, showcasing how Egyptian scientists are advancing photonics and radiation chemistry for strategic and technological applications. The absorption spectra of the glass samples reveal two main absorption bands, one in the UV region between 237 and 244 nanometers, the other in the near-infrared NIR region at 975 nanometers. As the ytterbium concentration increases, the intensity of the UV band at 237 nanometer decreases and shifts to a higher wavelength, while the 975 nanometer band increases in intensity without shifting in wavelength. The UV band is associated with oxygen deficiency centers, ODC, and non-bridging oxygen hole centers, NBOHC, changes in the valence state of YB2+, YB3+, caused by charge transfer processes, and subbands assigned to YB3+, charge transfer with oxygen ligands. Two main mechanisms explain this. 1. Charge transfer model, where YB ions switch between YB2+ and YB3+, with YB2+ being the origin of photodarkening. 2. ODC precursor model, where oxygen defect centers generate color centers responsible for photodarkening. There's also a smaller band at 385 nanometers attributed to bound hole polarons, which decreases with higher YB concentration. Meanwhile, the 975 nanometer band corresponds to YB3+ electronic transitions between the 2F7-2 and 2F5-2 Stark sublevels, a signature of strong electron-phonon interaction in the glass host. When the glass is irradiated with gamma rays at doses of 0.25, 1.25, and 10 kGy, interesting transformations occur. At 0.1% YB concentration, the 237 nm UV band shifts to lower wavelengths and decreases in intensity after irradiation. The 385 nm band shifts upward in wavelength and intensity at higher doses. The 975 nm band remains at the same position, but increases in intensity. At 1% YB concentration, the UV band around 240 nm shifts to lower wavelengths, showing reduced absorption with increasing dose. The 345 nm band shifts upward in wavelength and intensity, while the 975 nm band intensifies without shifting. At 3% YB concentration, the UV band at 244 nm decreases in intensity and shifts lower, while the 336 nm band shifts upward at all doses. Again, the NIR band increases in intensity but stays fixed in wavelength. The explanation is rooted in defect physics. Irradiation excites electrons, some of which are captured by YB ions, leading to healing of defects such as NBOs. This results in a decrease in UV band intensity, known as the photo-leaching effect. A new band at 700-800 nm emerges after irradiation, linked to ODC2 and NBOHC defects. Interestingly, this band almost disappears at 3% YB, suggesting a self-stabilizing effect at higher doping levels. Photodarkening is a major obstacle in ytterbium-doped laser materials. But here, the research provides a crucial insight. Higher YB concentration, specifically 3% YB, enhances the glass network's resistance to the formation of photodarkening centers. This happens because YB ions can capture irradiation-induced electrons and help reconvert non-bridging oxygens, NBOs, into bridging oxygens, BOs. This significantly reduces defect centers that would otherwise degrade laser performance. These findings strongly support the two main PD formation models and show how careful control of doping concentration and irradiation conditions can optimize laser glass for real-world use. Now let's look at the photoluminescence, PL spectra, which reveal how the glass emits light under laser excitation. The samples were excited at 915 nm and monitored at 1008 nm, producing two emission bands. 1. A high-intensity luminescence near 975 nm, linked to temporary YB2+ formation and rapid recombination. 2. A lower-intensity subband associated with permanent color centers related to broad absorption between UV and NIR. This process is governed by the equation YB3++ HN, YB2++ H. After 10 kGy of gamma irradiation, the PL spectra show, for 0.1% and 1% YB, the two bands are clearly visible and shift slightly. For 3% YB, the bands merge into a single broad emission around 990 to 1050 nanometers, indicating a more stable and uniform optical response. Interestingly, at 10 kGy, this broad band splits back into two, confirming the healing of some previously formed NBOs during preparation. This means gamma irradiation can enhance or stabilize the emission properties, making the glass more reliable for long-term laser operation. These findings are not just academic, they have real-world implications. By controlling YAB doping and irradiation dose, it's possible to engineer laser glass with reduced photodarkening, improved emission stability, and enhanced optical efficiency. The UV band behavior, emission stability, and defect healing mechanisms all point to the viability of 3% YB-doped phosphate glass as a cost-effective laser material. Producing this type of glass in Egypt can reduce import dependence, strengthen industrial and defense applications, and build national capacity in photonics and laser technologies. This research highlights how fundamental radiation chemistry and materials science can converge to create strategic technological assets for the country. If you've enjoyed this deep dive into cutting-edge Egyptian research, like this video, share it, and subscribe to For Science Salah Lotfy channel for more scientific stories that inspire innovation. Research by Professor Dr. Omnia Sallam and Professor Dr. Nagia Elalaily, Radiation Chemistry Department, National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, Cairo, Egypt. Published in Journal of Materials Science, Materials in Electronics, 2022.
Welcome back to For Science Salah Lotfy channel. We explored the preparation of ytterbium-doped phosphate glass, the effect of gamma irradiation on its optical absorption, and its photoluminescence behavior. Today, we continue this scientific journey with a deep dive into the electron spin resonance, ESR analysis, physical parameters, and final conclusions of this cutting-edge research. This work, led by Professor Dr. Omnia Sallam and Professor Dr. Nagia Elalaily, reveals how radiation technology can be used to engineer advanced materials for laser applications, with a direct potential economic and strategic benefit for Egypt. ESR, or electron spin resonance, is a powerful tool to detect defect centers and paramagnetic species in glass. The study revealed two ESR scenarios, depending on the ytterbium concentration. At low YB concentrations, 0.1% and 1%, the ESR spectra show signals attributed mainly to phosphate groups with three distinct components: P1, P2, and POHC. P1 and P2 are hyperfine lines related to phosphorus sites, 31P, I, Mus 1-2. POHC, phosphorus-oxygen hole centers, reflects the role of alkali ions in the glass network. As irradiation dose increased, more positive holes and electrons were generated, both from YB3+ ions and the phosphate matrix itself. This caused clear changes in the ESR signals, indicating defect formation and charge trapping. At higher YB concentration, 3%, a second scenario appears. ESR signals for YB3+ ions themselves are detected with G values around 1.9999, 2.018, 2.035 and 2.053 after 10 kGy irradiation. Some YeB3+ signals with GWAS8, typical of clusters, did not appear, suggesting a uniform distribution of YeB ions inside the glass matrix, without forming large aggregates. This is a positive indicator for maintaining optical clarity and minimizing photodarkening. Now let's examine the impact of gamma irradiation on defects in the glass. Gamma irradiation introduces energy into the glass structure, generating free electrons and holes. At lower YeB concentrations, this energy leads to more visible defect signals, such as P1, P2, and POHC. At 3% YeB, the signals become clear and well-defined, indicating more electron trapping by YeB ions and formation of stable paramagnetic centers. This behavior confirms that YeB3+ ions play a dual role. 1. Acting as sensitive detectors for structural defects. 2. And helping heal or stabilize these defects when exposed to radiation. The phosphate glass matrix, rich in Al, Na, Pb and P, provides a stable environment for ytterbium ions, preventing them from clustering and preserving the glass transparency and optical quality. The study also analyzed how irradiation affects the optical bandgap, E9, and Urbach energy, EU. The bandgap values decreased with increasing YeB content and irradiation dose. Meanwhile, Urbach energy increased, indicating a higher density of non-bridging oxygen sites, NBOs, and defect states. This tells us that adding YeB and applying gamma irradiation modifies the glass network, making it more flexible and enhancing its optical response. The Urbach energy curves and Tauch plots confirm this effect across different concentrations: 0.1% YeB, wide bandgap, fewer defect states; 1% YeB, intermediate behavior; 3% YeB, reduced bandgap, but controlled defect structure after irradiation. Now, let's look at refractive index and physical parameters. Refractive index is a key parameter for laser materials. The results showed a continuous increase in refractive index with increasing YeB concentration. This reflects more NBO sites, which increase the polarizability of the glass network. Other physical parameters, such as density, molar volume, molar polarizability, electron polarizability, and oxygen ion polarizability, also changed systematically. Density decreased slightly with increasing YeB content. Molar and oxygen polarizability increased, indicating a less compact but more optically active structure. Metallization factor remained low, showing the material maintained its dielectric and insulating properties while enhancing its optical functionality. These structural changes enhance the light-matter interaction, making the glass more efficient as a laser gain medium. The combined results of ESR, optical spectroscopy, and physical measurements point to a clear conclusion. 3% YeB concentration provides the best balance between optical activity, defect healing, and structural stability. Gamma irradiation at 10 kGy effectively stabilizes the glass by unlocking free electrons, healing NBO defects, and preventing photodarkening. These insights are crucial for designing high-performance laser materials that are cost-effective, easy to fabricate, and technologically impactful. For Egypt, this means reducing reliance on imported laser components, supporting national research programs in photonics, defense, telecommunications, and medical technologies, and strengthening the local scientific and industrial ecosystem. This research shows how strategic scientific work, combining radiation chemistry with materials science, can lead to real technological advances. Ytterbium-doped phosphate glass, optimized at 3% concentration and enhanced with gamma irradiation, is a strong candidate for future laser applications. To support more scientific breakthroughs from Egypt, make sure to like, share, and subscribe to For Science Salah Lotfy channel. Together, we bring scientific innovation closer to society and industry.
Dear viewers, this is Professor Dr. Salah Lotfy from the Egyptian Atomic Energy Authority, welcoming you once again on For Science Salah Lotfy channel. As we come to the end of this very special scientific presentation, I would like to express my deep appreciation and sincere gratitude to the outstanding Egyptian scientists who carried out this remarkable research on ytterbium-doped phosphate glass and its enhancement through gamma irradiation. My heartfelt thanks go to Professor Dr. Omnia Sallam, Professor Dr. Nagia Elalaily from the Radiation Chemistry Department, National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, Cairo, Egypt. Their work represents a valuable scientific contribution to the fields of laser materials, radiation chemistry, and advanced photonics. This research is not just an academic achievement, it is a strategic step forward for Egypt. By developing high-performance laser glass locally, we reduce dependence on imported materials, build national capabilities in photonics and radiation technology, and open the door for future applications in medicine, communications, defense, and industry. The use of gamma irradiation to heal structural defects and improve the optical properties of ytterbium-doped phosphate glass is a powerful example of how science can serve practical national goals. Such scientific excellence deserves recognition, encouragement, and support. I would also like to extend my warm thanks to all of you, our viewers and followers, for your continued support of For Science Salah Lotfy channel. Your engagement gives great value to this platform. I invite you to share your thoughts, questions, and comments about this research in the comment section below. Together, we can enrich the scientific dialogue and encourage more brilliant minds to contribute to Egypt's future in science and technology. If you enjoyed this episode, don't forget to like, share, and subscribe to stay updated with more pioneering Egyptian research. Thank you all, and special thanks once again to the researchers for their outstanding work.